I swear to God, nobody can agree on how to pronounce this dude's name. Is it Kirchhoff? Is it Kirchhoff? Is it Kirchhoff? Seems like no matter what way I pronounce it, I always get corrected, so I'm about to just start calling him Gustav. But anyways, back in the 1840s, my buddy Gustav spent a whole bunch of time trying to figure out how to explain electricity to all you window lickers, and in doing so, he came up with a couple of laws, one of which was Kirchhoff's voltage law, which I've done several videos on, the other of which was Kirchhoff's current law. Excuse me, Gustav's current law. So anyways, you can see that Gustav's current law states that the total current entering a junction or node in an electrical circuit is exactly equal to the total current leaving that node. This means the algebraic sum of all currents in any node must equal zero. So to put it in dum-dum terms, what goes in must come out, nothing more, nothing less. So what my buddy Gustav is saying is that if you have a point in the circuit where you have two paths entering that point and one path leaving that point, the amperage of A plus the amperage of B plus the amperage of C equals zero. Well, how is it possible to add up three values and equal zero? Well, it's important to understand which values are positive and which values are negative. If the current is entering the point, then it is a positive, and if it is leaving the point, then it is a negative. So in this case, if we have 7 amps entering on this path, 2 amps entering on this path, and 9 amps leaving on this path, then 7 plus 2 plus negative 9 equals 0. This is a lot easier to explain with DC because with AC it changes direction 120 times per second. So if this were an AC circuit, we would just need to hit the pause button and freeze time for a minute. And whatever the polarity is in that given moment will dictate the positive or negative of our value. And if this still isn't making much sense to you, how about we set up a little demonstration? So here I got two incandescent bulbs that are wired in parallel. This one's a 7.5 watt and this one's a 25 watt. This wire nut right here will represent our node or our point on the system that we're going to refer to for Kirchhoff's current law. Right here on this wire, so this incandescent bulb, we're drawing 0.06 amps, so 6/100ths of an amp. This one right here, we're drawing 0.18 amps, so 18/100ths of an amp. And then on this wire right here, 0.24 amps. So as you can see, the current entering any point on the system equals the current leaving that point of the system. To put it in dum-dum terms, what goes in must come out, nothing more, nothing less. Little side note, I'm actually pretty excited right now. I just went and dug this clamp meter out of my storage unit. This is the only clamp meter I own that can do DC amperage, so stay tuned, I'm going to do something with that. Anyways, hopefully this makes a little bit more sense. If you guys have any more questions, you can always DM me or drop it down in the comments below.